do today is we're going to do a lot of lemmas on expectation, and then we're going to start to see some applications. So the goal is to do some of the applications today and just give you a sense of the power of these methods. And then on Friday, go into some even more powerful applications of this idea, as well as review some of the material we've already done. So we'll have some big applications on Friday. I deliberately am not giving you what they're going to be so that it'll be a surprise and you can try to think about what they are live on the fly. Okay? If I had an infinite amount of time to teach this class, I would probably have a month on linearity of expectation. It is amazing how many things this can do. We don't have an infinite amount of time. I don't have a month, so it's going to have to be very quick and brief. So a couple of lemmas on expectation. So I'm not going to prove all of them. A lot of these are straightforward. So one, if y equals ax plus b, a and b are constant, then the expected value of y is equal to a times the expected value of x plus b. Okay? Basically, think of it as I'm shifting everything by b and I'm rescaling my units. And this just tells you how things transform. So it transforms exactly as you would expect. The proof, and I'll just start to write and then I'll erase, is we want to find the expected value of y would be the integral from minus infinity to infinity of y, fy of y dy. And so now we just have to figure out how is y related to x. And so I'll leave this as an exercise. This is a good way to check your proof skills. If big Y takes on value little y, then big X takes on value little x. And we can express this in terms, and you can do the calculation. So I'll leave that as an exercise. All right, so that's the first of the lemmas I want to do. The next one is the more interesting one. If x and y are independent, then the expected value of xy equals the expected value of x times the expected value of y, and is an extremely important special case. The expected value of x minus its expected value times y minus its expected value equals 0. There are two ways to try to attack this part. One way is to say, well, I have an expected value of a product. I can expand everything. And when I expand everything, one of the terms will be the expected value of x times y. Another will be the expected value of negative mu x y. The negative mu x is a constant. It comes out. And I'll get negative mu x times the expected value of y, which is just mu y. And similarly for the other two pieces. So one way to attack this problem is to just multiply it out, see that you have 4 pieces, and do the analysis like that. What's the other way to try to do this, the second part of this lemma?
Another way is that you could look at the two terms being multiplied.
Okay.
And figure out what their expectation is.
Okay, and why will that help us?
Because you get the expected value of x minus the expected value of the expected value of x, which is just the expected value of x minus the expected value of x.
You're close. You're not quite phrasing it quite right. You want to use part 1. Right? So if we call this I and this II, we'd like to just say, well, let's just replace over here. For x, replace x minus its expected value. Replace for y, y minus its expected value. What do you have to justify if you're going to do that? Okay, that's by definition, so that's not a problem. Good. If x and y are independent, then x minus mu of x and y minus mu of y are independent. This is very similar to, there was a homework problem where we had, if x and y are independent, are x complement and y complement independent? And one way to do this is you first say x and y are independent. And then x and y complement are independent. If you take the complement of 1, it's independent. If it wasn't the case, then if x and y complement are independent, well, if I know y complement, I know y. And so you just do a successive of complements. You would do x, y, then you would go to x, y complement, then you go to x complement, y complement. Or we might have called them a and b. So if you want to use part 1 here, you have to say if x and y are independent, if I shift x by a constant, it's still going to be independent. And then similarly, if I shift y by a constant, it's going to be independent. I can do that in 2 stages. Okay? So we will see that 2 is extremely important. The reason it's so important is it allows us to split a product, a 2-dimensional object, into 2 one-dimensional objects. So instead of having a double integral, we have 2 single integrals. This is a huge gain. So here, however, we have a much stronger condition. We have if x and y are independent, then this is true. So as soon as I say independent, what do you know about the joint PDF? So the joint PDF is the product of the marginals. So do you think that's going to have anything to do with the proof? Yeah, because the joint PDF splits, the integration is going to factor and it's going to split into 2 different integrals. So for the proof, so the long way we can do this is we can say, let's let z equal x times y. And then the expected value of z would be the integral from minus infinity to infinity of z fz of z dz. If I want to be extreme overkill and try to fill up 50 minutes today, this is a great way to start. Right? I give you my random variable, and this is the definition. Well, this is really the same as the expected value of xy is the integral of xy f xy xy dx dy. Minus infinity to infinity, minus infinity to infinity. Well, now if this joint density function splits, then this becomes the integral from minus infinity to infinity of x fx of x dx, integral minus infinity to infinity y fy of y dy. And now that's going to just be expected value of x, expected value of y. And that's the proof. So the product of independent random variables is the expectation of the product is the product of the expectations. What word would you love to remove from the statement? Independent. So do you think it's true if I remove the word independent? Is the proof maybe just harder? Okay, so you're shaking your head. Why not? I'm lazy. I've got 2 kids. I'm sick. I have lakes to deal with at the end of my driveway. I don't have time to prepare a lecture. I'm going to do a simple proof and leave the hard case to you. Yes?
We know that can't be the case because the expectation of x squared definitely does not equal the expectation of x.
So consider y equals x. Then the expectation of xy, if true, would be the expected value of x, the expected value of x. Or the expected value of x squared is the square of the expected value. So all you have to do is choose a random variable that has mean 0. And you'll see that this is absurd. So take x to be uniform, say on -1/2 to 1/2. Then the expected value of x will be 0, but the expected value of x squared will clearly not be 0. Another good example, potentially, is to take y equals, any other good thoughts? It's not as good as this, but there is another one that might be worth looking at. I'm sorry?
1 over x?
Yeah, 1 over x. Why are you a little hesitant with 1 over x?
I don't know. I was just thinking that's a different one.
No, 1 over x is exactly the one to look at, because now the product is going to be 1. I want to try to find things where I can calculate the left-hand side easily, or I can deduce things about it. Again, most of you are never going to use this class. But the ideas of how to approach mathematics, I'm hoping that will be useful in whatever you do. Okay? I want this left-hand side to be calculable. If y equals 1 over x, I'm making the left-hand side as easy to calculate as possible. Now, this side over here becomes a little bit hard, and I've got the expected value of x, the expected value of 1 over x. The right-hand side now is a mess. Maybe it's true, maybe it's not. But you could try maybe take a uniform variable on the interval 1, 2, see what you get. And now look at the, so there's work to be done, but this is a good case to look at. So it's all coming down to, can I find special cases? And if so, what special cases? If I take x equals y, then this side over here is going to be the expected value of x squared. Well, I don't know exactly what that is. I know it's non-negative. If I take y equals 1 over x, I know it's the expected value of 1. I can calculate that easily. All right, so unfortunately, the word independent is crucial here. If we remove this word, the result can fail violently. OK, so this is your two key lemmas about expectation. What we're going to do now is we're going to start preparing for the central limit theorem and problems. We're going to look at sums of random variables. Which sums do you think will be the easiest to analyze? What kind of sums?
Finite sums?
Finite sums, OK. What kind of finite sums? Finite sums of independent random variables, and in fact, finite sums of identically distributed random variables. All right, so let's let x, we'll let x, why not? X will be a1 x1 plus an xn. The ai's are constant. The xi's are random variables. Then what do we know about the expected value of x? We've actually already proved this. So what's the expected value of a sum? The sum of the expected value. So it'll just be a1 expected value of x1 plus dot 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 plus an expected value of xn. And we'll see later that this is incredibly useful. The harder one is, what is the variance of x? So let's try to sniff it out. The variance of f of x should depend on these quantities. What do you think the variance of x depends on? Yes? Say that again? OK, so the variance of each individual xi. It seems reasonable that the variance of x should somehow be a function of the variance of the xi's. What else should go into the formula?
All of our coefficients.
The coefficients probably have some role to play in the formula. How do you think the coefficients come into the formula?
They should be squared because the units of the variance are squared.
Good. So let's look at special cases. If we look at the special case, so the answer, it's going to be a1 squared variance of x1 plus an variance of xn if independent. And so let's get some idea of why this is reasonable. Imagine all the a's are 0 but the first one. So I have a really simple case where all I've done is I've rescaled x1 by, say, 5. If I've rescaled x1 by 5, I should increase the standard deviation by a factor of 5. The variance is the square of the standard deviation. It should increase by 25. So it seems reasonable that there should be a1 squared through an squared coming into play. You could have absolute values, but the units would be wrong. It wouldn't scale properly. The other thing is, if a1 were negative, let's say a1 is negative 1. Does that change the variance? Does x1 and negative x1, do they have the same variance? They have the same fluctuations about the mean. All I'm doing is I'm looking at the mirror image. I'm flipping it over. And so if I multiply all my quantities by -1, I'm not changing the variance. So I don't expect the sign of these coefficients AI to play a role. Unfortunately, this is only the case if things are independent. If things are dependent, you have cross terms. You have the covariance terms. So the question is, how do we get this? So one of the ways we get this is there's lots of different formulas you can use to calculate variances. So the variance is the one that's hard here. The other one we've actually already proven. So we want to calculate the variance. Well, we can go back to the definition. So proof. All right, so the first thing is we're going to let x be a1 x1 plus an xn. The mean of x is going to be a1 mu1 plus an mu n. All right, so now if I want to calculate the variance of x, by definition, this is the expected value of x minus its mean squared. All right, so this is the expected value of a1 x1 plus an xn minus, I'll put this in parentheses, a1 mu1 plus an mu n, put more parentheses, put a square, close the bracket. Okay, long expression. This should be screaming something to you. What is this screaming at you to do? When you see an expression like this, what do you want to do algebraically to this expression? I'm sorry? So one thing is to try to put the e through. But before you put the e through, you should, OK, so this is probably a good time to mention my favorite New England transcendentalist writer, Henry David Thoreau. He is the patron saint in my mind of mathematics. Okay, what sage advice does Thoreau have for us? Actually, the full quote, please. Yeah, which should be simplified to simplify, but I think he's doing this to emphasize a point. Simplify, simplify. When in doubt, simplify things first before you do any work. Looking at this expression, how should we group things? Yeah, group the a1 x1 with the a1 mu1. Put all that stuff together first. And before we do any of the analysis, let's put the terms together. And so if we start to do that, we now get the expected value. Now we'll have lots of ways to write it. I can write it as this. I guess a1 x1 minus mu1 plus a2 x2 minus mu2 plus an xn minus mu-n squared. What's nice about this is now looking a lot like what I erased a few moments ago. When I expand this out, I'm going to get a lot of cross products. So I take everything and I multiply it by itself. And then I take the expected value. So I'm going to have each term hitting itself. And I'm also going to have cross terms. So when you multiply everything out, we're going to get the following. It's going to equal the sum, I goes from 1 to n, of ai squared, expected value of xi minus mu I squared, plus a sum I does not equal j, ai aj expected value of xi minus mu I, xj minus mu j. Bless you. There are lots of ways to write this. You can write this as I does not equal j, or you could write it by symmetry as twice I strictly less than j. I prefer to write it as twice I strictly less than j because I've decreased my sums by a factor of 2. So in terms of how many things I'm computing, this is a little bit faster. Now again, this should be screaming at you why you want things to be independent. If things are independent, what do we know? 0. So 0 if independent. So therefore, the answer is going to be the sum I goes from 1 to n of ai squared variance of xi if independent. If not, have what's called covariance terms. All right. So notation is supposed to be good. The reason this is called covariance is it's very similar to variance. Right? We actually understand this term perfectly if I equals j. If I equals j, this is just the standard variance. If I does not equal j, it's the covariance. It's how xi and xj are varying together. Okay, so we have a particularly simple formula in the special case when the random variables are independent. In the general case, it's going to be a lot harder because we're going to have to analyze that piece over there. Okay, any questions about this expression, how we got here? All right, so I will leave you to read in the book about how you would get the covariance and how you would define the covariance term here. There's a lot of results you can say about the size of the covariance term. You can bound it in terms of the size of the variance of the two different quantities. There's some control as to how large it can be. Are there more variance terms or covariance terms? So how many variance terms do we have?
You mean inside the summation or?
Just total. How many variance terms and how many covariance terms in this expression? Total number. So we have n variance terms, and how many covariance terms? Either n choose 2 or 2 times n choose 2. It's on the order of n squared. There's a lot more covariance terms. So you've got to be very careful in terms of what's going on. Most of the contribution could be coming from here. OK. So the last result I want to just quickly state is, let's see if I can go all the way down here, almost. All right, so the last result I want to quickly state is, is a nice expression to calculate the variance. OK, so formula for the variance. We are told the definition is that the variance of x is the expected value of x minus mu of x. I'm going to write mu of x as expected value of x this time. So this is the definition of the variance of x. After some algebra, it turns out that this is the expected value of x squared minus the expected value of x squared. It's essentially measuring what happens if you move the square from inside the expectation to outside. In general, does order matter in life? Does it matter if you put on the bulletproof vest and then I shoot you, or I shoot you and then we put on the bulletproof? Okay. Most of the time, order matters for things. If you want to think of compound interest, a less violent example, does somebody add money to your bank account and then the bank calculates the interest, or does the bank calculate the interest and then does it compound? The order at which events happen typically matter. The expectation of a square is typically not the square of the expected value. And in fact, this is a great way to quantify the difference. Now, here's a fascinating result. What can you tell me about this difference?
If x is somehow independent of itself, it equals 0.
Yes, but more generally, what can you tell me about this expression? What kind of number must this be?
Or non-zero.
Non-zero. It's got to be non-zero because we're taking the expected value of a square here. The square here can't be negative. So we're taking the expected value of square. When you look at a probability distribution function, here's a really hard question I could have asked you. Is there a probability density function such that its second moment is smaller than the square of its first moment. It turns out that's not the case. This relation always holds between the first and the second moment. This leads to a very interesting question. If I give you a sequence of numbers, when are those numbers the moments of a probability distribution? Here's at least one condition. I believe the general result is known as Hamburger's theorem as to when a sequence of numbers uniquely determines a probability distribution. So this is an unexpected result, but it's a nice consequence of this. The way you would prove this is you expand the square, and then you use linearity of expectation. And you'll have expected value of x squared minus 2 expected value of x times x plus the expected value of x squared. So I'll leave that as an exercise for you to go through and prove this. OK. Any questions on the formula for variance? All right, so we've got a lot of theoretical results now at our disposal. Let's actually use them to study something that's useful. So in order to have applications, we need some random variables to look at. So right now we have not formally defined any random variables. There are some very natural choices to look at. And in some sense, we've looked at them already this semester. We just haven't isolated them and giving them a name. So Bernoulli random variable. I am sad to admit I don't remember exactly which Bernoulli this is named after. There are a lot of famous Bernoulli mathematicians. So we say x is Bernoulli p if the probability x equals 1 is p, the probability x equals 0 is 0. What should you be thinking of when you see this? Does this remind you of anything you've seen?
Do you mean 1 minus p?
Probably I mean 1 minus p, yes. Sorry. All right. Now that it's correct, what does this remind you of? Where have we seen something like this?
Question number 7.
Well, give me something specific. We don't have to go detailed like that. Where have you seen something like this? Coin tosses, right? Think of this as a coin toss. We get a head with probability 1, we get a tail with probability 0, but we don't want to say things like heads and tails. Those have been copyrighted. We'll say 1 and 0. Okay? Why do we like 1 and 0? It's not because they've been copyrighted. Why do we use 1 and 0? Because we can add them. And we're actually going to see applications of adding them now. Let's do binomial random variable. So we say x is binomial NP if the following. The probability x equals k is n choose k, p to the k, 1 minus p to the n minus k, if 0 less than equal to k less than equal to n is an integer, and 0 otherwise. OK. What does this look like?
How many ways can you get exactly 3 heads when you toss a coin?
Sure. So we're now tossing a coin with probability p of heads n times and counting how many successes we have. OK? So let's start doing some calculations. One of the things about mathematics is there are certain questions you just instinctively ask. When I give you a random variable, there are some questions you should immediately ask about that random variable. What's the first question you should ask? Or at least one of the top ones you should ask. So what would you want to know about a random variable? You can get one piece of information from me. If you want to pretend you are a med school pre-med major, what one piece of information would you like? The average, right? If I give you a random variable, you want to know what's the average value, right? Why? If I have one number to give you, that's the best number I could give you. If I could give you 2 numbers, in addition to average, what would you like? Standard deviation. So here, let's calculate the expected value of x. So the expected value of x, this is not that bad of a calculation. It's going to be p times 1 plus 1 minus p times 0 equals p. If I want to calculate the variance of x, there's several ways to do this. I'm going to use the formula we just proved here. It's the expected value of x squared minus the expected value of x squared. So expected value of x squared minus the square of the expected value of x. What's the expected value of x squared? I'm sorry? The expected value of x squared. If I put it in a square here, I get 1 squared, 0 squared. There's no change. It's still p. So I get p minus p squared, or p times 1 minus p. Why am I writing it as p times 1 minus p? This is a really good way to write it to see what's going on. It's the product of the probability it happens and it doesn't happen. So again, it's just a calculation. All right, in the interest of fairness, I'll let you guys do the other one. Let's calculate the expected value of x in this case. So we need to calculate the sum, k goes from 0 to n, of k times n choose k times p to the k 1 minus p to the n minus k. All right, I did that one. You guys do this one. Am I being fair? What's wrong with this? It's a mess, right? You've got a k down here. You can try to play some games, expanding out the binomials, canceling things, trying to rewrite it, trying to understand it in terms of a simpler process of maybe a binomial with 1 less n. But this is a nightmare because you now have a polynomial times a binomial times a changing factor here. Okay? It turns out if you can do the Bernoulli calculation, you can do the binomial calculation. What's the connection between the two? So how are the two processes related? How can we understand the binomial in terms of the Bernoulli? So somebody tell me in words what the Bernoulli is doing. Do you have it?
It's just the sum of Bernoulli random variables.
Good. What kind of Bernoulli random variables? Independent, identically distributed. Right? This is our favorite type of random variables. So if xi is Bernoulli p, then x1 plus xn is binomial np. Each one of these is an independent toss. What we're doing is we're expressing a complicated process in terms of a bunch of simpler ones. If I want to calculate the expected value of x, this is just the expected value of the sum. But the expected value of a sum is the sum of the expected values. This is linearity. It's the expected value of x1 plus the expected value of xn. So we get p plus p n times p. And if you think about this, this is exactly what you would expect. If you're flipping a coin with probability p of heads, you would expect if you flip it n times that you have np heads. And if you want, you can try to think a little bit about how you would find the corresponding probability for how many tails you would have. It has to add up to 1. In the special case, when p equals 1 minus p, it has to be n over 2. This is an extremely reasonable formula to have come out. We can calculate that sum very easily. What about the variance? Do you think we can calculate that easily? What do you think? Why can we calculate the variance easily?
Because they're independent.
Because they're independent. So because they're independent, I'll erase this and I'll just write, this is just NP. The variance of x is the variance of x1 plus xn. It's going to be n times the variance of any of the xi. So it'll be np1 minus p. And if you do it the long way, it's the sum, k goes from 0 to n, of k minus np squared, n choose k, p to the k, 1 minus p to the n minus k. If this doesn't convert you to linearity of expectation, I'm out of tricks. All right? We've completely bypassed having to do this nightmarish sum, and we've reduced it to simple things. If you think back to like your chemistry, your physics classes, where you break things up into the constituent pieces and then you see how they combine, that's what we're doing here. Our constituent pieces are not atoms. Our constituent pieces are independent random variables. And by understanding how they behave, we can combine them and understand things in great detail. All right, so this is the power of linearity of expectation. We're able to even handle the variance in this case. We've got some nice formulas that we're able to do. This stuff all falls out immediately. There are other ways to do this, and this is similar to some of the sums some people got when they looked at some of the processes on the exam as infinite processes. There's a method called differentiating identities. It's one of my favorite techniques in mathematics. That's chapter 11. We will get to that. And it's another way to evaluate these sums. And what's nice about that is equalities in mathematics, these are hard to come by. If you have a method that takes as input an equality and generates infinitely many more equalities for you, that's beneficial. OK, any questions about the linearity of expectation here? OK, so what I want to do now is I want to talk a little bit about convolutions, just to start the conversation there. We've already seen them a little bit. And so the idea of convolutions is if I have two random variables and I have densities for them and I combine them, I should be able to figure out what the density of the sum is in terms of the constituent pieces. And the question is, how do we get this? So we've already, is it no longer working? Oh, it's no longer working, so this is interesting as to, all right, so I'm going to try to see if we can get this to keep working. So in terms of doing the I'm going to give you two random variables. Do you think we want them to be independent or not independent? Independent. It's going to make things a lot easier when things are independent. Okay, so the more independent things are, the harder the calculations are going to be. So now let's consider the following. Convolutions. So let's say x has density f of x, y has density f of y, and we'll let z be x plus y. And so we want to find the probability density function of z. All right. So we look at what x is. If I want x plus y to equal little z, if x equals little x, what does z have to be? So I want x plus y to equal z. If x is little x, what should y be? Z minus x. So this becomes the integral. X goes from minus infinity to infinity of fx of x, fy of z minus x dx. And now x plus y equals z. There's a longer way to get this. I could look at the cumulative distribution function of z. This is the probability that big Z is less than or equal to little z. And how would I write this? Well, again, x can go anywhere from minus infinity to infinity. And now what's the range for y? If I want x plus y, if I want z to be at most little z, how large can y get up to? Y goes from minus infinity up to
Z minus infinity?
not z minus infinity, to z. Because now x plus y will be at most z. Well, nope, can't be z. So it's going to be a little bit different than just z. What's the largest y can get up to? Z minus x. So now dy. So this will give me the cumulative distribution function of z, the probability that big Z is at most little z. I look at all pairs x and y such that x plus y is at most z. So if I'm looking at it, you're going back to Calc 2, here's my x-axis, here's my y-axis. If I want x plus y equals z, that's okay. That's going to give me a line. So I should get, I don't know, something like this, I think. And I'll have some region like this. And I need to integrate over this space. And so I'll have this two-dimensional integral. How do I get a density from a cumulative distribution function? How do we go from this to the density? Differentiate. There's a reason why I'm using capital F and little f. I'm trying to remind myself, take the derivative. So I have to take the derivative of this. All right, so now I need to justify, I pass the derivative through the x integral, and now I take the derivative of this. And so if I now take the derivative with respect to z, d by dz of fz of z will be the probability density function. It'll be the integral x goes from minus infinity to infinity. Now I take the derivative with respect to z of the following. It's going to be big Fy, the antiderivative of this, evaluated at z minus x, minus the antiderivative evaluated at negative infinity. And then I multiply this by fx of x dx. What is big F of y at minus infinity? 0. It's a cumulative distribution function. Even if it wasn't 0, it would be some constant. When I take the derivative with respect to z, no problem. When I take the derivative of this with respect to z, the derivative of big F is little f of y. Evaluated z minus x, then I take the derivative of the inside piece with respect to z, which is just 1. And so when I do the derivative, I get x goes from minus infinity to infinity. I'll put this back in the right order. Fx of x, Fy of z minus x dx. What's important to note here is I never need to know exactly what big F of y is. This is theoretical math at its best. Hey, there's some function, call it big F of y. We don't need to know exactly what it is because we're never going to use it. We're going to immediately take its derivative and go back down to Fy. And so this is a way to justify this formula. So this is called the convolution. And we write it as fx star fy, put parentheses around it, and then put a z in here to say where we're evaluating it. So it's the convolution of these two quantities evaluated at z. You can define the convolution for any functions. For us, we will only use the convolution when fx and fy are densities. Okay? So this is the convolution. This is the definition. This is a longer justification as to why that is the definition. All right. So let's think about some properties. So we know the convolution gives us the density function of the sum. So questions. What questions do you have about the convolution? What would you like to know? What kind of properties would you love to have true? We have fx star fy. What might you be interested in?
Expected value.
So one is what happens to the expected value. But I'm talking about fx star. OK, so what if I switch them? So question 1 is fx star fy equal to fy star fx. Does order matter? There's the long proof, the roll up your sleeves proof and say, well, let's write down fx star fy, let's write down fy star fx, let's change variables and show the two are equal. That's the long algebraic proof. It's not enlightening. At the end of the day, the algebra works out and they come out equal. There's a very enlightening way to look at this from a higher perspective and see why it has to be true. What is fx star fy? What's the interpretation of what this gives us? What is this giving us? What quantity? I'm sorry? F of z. And what is z? Z is the sum. So this is the density of x plus y. What's this giving us? Density of y plus s. Okay. Now is it easy to prove that the convolution is commutative? Yes. Because addition is commutative, convolution is commutative. Addition commutative implies convolution is commutative. To me, that's the better way of looking at what's going on. Is from over here, yes, we could do the long algebra approach, but there's no need. We can do it much faster by saying there's an interpretation of what's going on. The convolution is the density of the sum. Well, if I sum the stuff in the opposite order, I'm going to get the same density. If I had 5 sums, it doesn't matter what order I sum them. Intermediate steps could be different. All right, so we have a relationship that's commutative. What other questions might we want to know about it? What's the next thing you might ask? So fx star fy star fz. Is this well defined? Not initially. Convolution takes 2 inputs. So there's 2 possibilities. Maybe I mean this, or maybe I mean this. Do you think it matters? No. This is x plus y, and then add z. This is y plus z, and then add x. So they're equal, and you have associativity. So there's a lot of properties you would expect to have. So how many of you have taken abstract algebra? I actually have to keep my hands down. I never actually took abstract algebra. Somehow got through the math major. So if you take an abstract algebra course, I've been told you learn about things called groups. And groups have a couple of properties. They have associativity, right? They have an identity element. They have inverse elements, and they have closure. So you can start to ask, is there a big structure lurking in the background here? What would be the identity element? Any thoughts as to what might be the identity element? So what would 0 be? It would be the random variable where you have a 100% chance of getting 0. So it would be a huge spike. So it would not be a continuous probability distribution. All the mass would be concentrated at one point. And so they call that the Dirac delta functional or the Dirac delta spike. There is a way to put in something like this and have a nice system along these lines. Okay, so there's a lot of stuff that we can do with convolutions. And there are a couple of examples in the book as to how you would do these calculations and get nice closed form expressions. In general, however, the more convolutions you try to do, the more nightmarish the results are going to get, and the harder it's going to be to get a nice closed formula. What will we use instead when we have lots and lots of convolutions? We're going to try to invoke the Not linearity of expectation, but a really good guess. What is the thing we're aiming for in the class we're going towards? The central limit theorem. The central limit theorem will somehow convert the density of these to something manageable. And it turns out that there's a really nice process that takes convolutions and converts convolutions to multiplication. And that's a miracle. Multiplying is easy. Convolution is not easy. This is integration. You want to avoid integration whenever possible. Okay, so this is a good place to stop for today.